All right, welcome to another rendition of me talking to myself in my room about geology, day 26, volcanoes and their hazards, as well as some more about igneous geology. But before we get started today, I want to go over some logistics like we usually do. Okay, so just a couple of reminders. We have several things due this Sunday, March 29th by 11:59 p.m. Um, you have two reading quizzes, chapters 4 and 5, right? 4 is about magma and igneous rocks, and chapter 5 is about volcanoes. You also have to complete the very short lecture quizzes on Blackboard that I post that are associated with each of these lectures that I do. And then you also need to complete Lab 7, which is posted on Blackboard as well, where you explore different volcanoes in Google Earth. And so some of you who have started this last Monday when I posted it, or yesterday, have emailed me that you can't quite do all the questions yet. That's okay. We haven't gone over all of the material yet that we cover in the lab. So today we'll talk more about volcanic hazards so you understand a little bit better how to do that assignment. But you should be able to go in and measure all the different characteristics of the volcanoes without more additional lecture material. Okay, and then I'll just remind you that this is, it looks like quite a bit of work, but if you spread this out over the week and stay diligent with it, that'll put you in a better position where you don't feel like you're scrambling on Sunday. I know that this shift to remote teaching, a lot of professors are still trying to figure out how to make this manageable for you guys. I've tried to reduce the workload in this class compared to normal and give it as much flexibility as possible. So we'll see how Lab 7 goes and go on from there. Okay, so let's go back to igneous rocks just for a second and think about the two different types that form, right? So this is a review from the last few classes, is that we have igneous rocks that are either extrusive or volcanic, meaning they form through eruptions on Earth's surface, or we have intrusive or plutonic rocks, those which form below Earth's surface, right? So volcano, Roman god of fire, Vulcan, explosive or extrusive eruption like the volcanoes in the Andes, versus a plutonic intrusion like Pluto, the Roman god of the underworld, right beneath the surface. And those result in these giant like igneous landscapes called batholiths, like Yosemite Valley, okay? And we also want to remember that the igneous rocks that you may go out and pick up off the ground, right? By looking at that rock and understanding its chemistry as well as where in the earth it formed, tells you about the different type of environment that was present there. Okay, so the environment in which these igneous melts cool into rocks is places a control on how quickly or how slowly that melt cools, which governs how large of crystals you result in, right? If you cool something very slowly, a crystal can grow very large, but if you instantly quench something in a cold temperature, you're just going to get glass. It also controls the shape and the morphology of the rocks that you get, and as well as the entire landscape, right? The type of volcanic landscape that forms is really governed by these different environmental controls. And then the magma chemistry, right? Specifically, how much silica is in a melt determines the type of igneous rock that'll form, going from the least amount of silica, which is a basalt or gabbro, up to the highest silica content, which is either granite or rhyolite, okay? And the magma chemistry controls the viscosity of the lava that's erupted at the surface in an extrusive environment, and that controls the behavior of lava. Whether you have the low viscosity basaltic lava flows that flow like thin pancake batter versus thick, highly viscous lava flows that are like, like really thick cake batter or something, okay? So again, looking at this diagram here, I just want to reiterate that, right, we have differences in the cooling rate. If you are deep down towards Earth's interior in a magma chamber, it's going to cool more slowly and you'll get greater grain sizes. And as you get up towards the surface where it's colder and things erupt into the atmosphere or as lava flows, you end up with really small grain sizes or glassy texture. Okay, and then the amount of silica content determines whether a igneous rock is mafic, if it has low silica and relatively high amounts of magnesium and iron, or if it's a felsic rock, which has very high amounts of silica and feldspar in it. Okay, so last day we talked mostly about extrusive igneous environments because I wanted you to get going on the volcano lab, but I want to go back beneath the Earth's surface and talk about the different types of intrusive igneous settings that can form. And so the first one we'll talk about are tabular or sheet intrusions. And these can take on two main categories. And this is based on the orientation of how those intrusive rocks penetrate into overlying rocks. So if you have a sill, that is where you have a mostly horizontal intrusive rock that goes in between like the layers of sedimentary rocks or other horizontal planes in below Earth's surface. If you have a rock or intrusion that cuts across layers and goes mostly vertical, we call that a dike, okay? So in this diagram down here, it's showing how we have a, let me get out the laser pointer. Okay, so here is a vertical intrusion of magma, which turns into a dike when it cools off. And here is a horizontal plane of magma that has intruded and is cooled into a sill. So if you got rid of all the surrounding rock that was not part of that intrusion, you'd be left with something that looked like this, right? It's kind of like if you if you had like a cake or something and you got a syringe from beneath it and inserted a bunch of like frosting into the middle of the cake or something, right? Okay, it's an intrusion. So I'm just going to show you guys some pictures from Antarctica where in the dry valleys of Antarctica where we have this really spectacular landscape that because there's no trees that get in the way of seeing the geology, we can see this amazing igneous environment where you had these huge Ferrar, it's called the Ferrar dolerite, which is a type of gabbro that intruded in between these layers of really bright white sandstone and left behind these sort of chocolate colored sills, like this giant one. Fun fact, I spent the night right there in 2014 on accident when a storm rolled in and a helicopter couldn't come to get us and slept on the ground. That was not very much fun. But anyway, got to see some cool pictures of sills from that. And then sort of nearby here, you can see where these intrusions of dolerite went nearly vertical, and these are examples of dikes, right? They cut across the layers of the rock. They don't go in between the layers. So how do we actually form sills and dikes? Okay, so sills and dikes form when you have weaknesses in the pre-existing rock, typically weaknesses that are exploited by extension or stretching of the landscape. When you stretch something out, right, you're pulling it apart and you allow things to snap and crack in the middle. And when you create those cracks and fractures, now magma that's rising up from beneath can fill those cracks and intrude between them. So if you have stretching out away from across the landscape, you might get vertical cracks that form and allow dikes to intrude. Or if you have a sort of similar situation where you have weaknesses that are horizontal in the rocks, a sill could intrude horizontally between bedrock layers. Okay, so these are like the two most basic types of igneous intrusions that you can go out in the field and observe. but they come in other shapes and forms. And so another example of this is a laccolith. So a laccolith is a type of igneous intrusion where you have some little bike of lava that flows up and it keeps flowing up, and then it finds a spot where it can just start accumulating between bedrock layers, sort of like a zit. It's gross, but it's like this buildup of magma between layers that causes bulging. So there's a really famous laccolith in Wyoming, and it's called the Devil's Tower. And if you have seen Close Encounters of the Third Kind, this is sort of like the landmark that's in the middle of it. So this whole movie is about Richard Dreyfuss, this crazy guy who gets this vision of Devil's Tower in his mind. He's abducted by aliens. There's Devil's Tower. And he goes on this whole quest, and he's like, oh, I must find the laccolith. Oh, I'm climbing up this laccolith. Oh, there's a helicopter chasing me on this laccolith. Don't let me go off of this laccolith. Oh, there's another laccolith. Oh, I'm drawing my laccolith. Now I'm making it out of mashed potatoes. Now I'm drawing it with charcoal. Now I'm making it with clay. Oh, now I've built a life-size model of a laccolith. My wife loves a laccolith. Look at that laccolith. Wow, I finally found my laccolith. Gosh, isn't it a beautiful laccolith? Wait, the government knows about the laccolith. Why is the government wondering about this laccolith? Oh my god, aliens know about this laccolith. Wow, who knew? Laccoliths bringing the people, aliens from outer space, all together. All in the name of igneous intrusions. Okay, so you guys are probably having a lot of spare time on your hands now, and you should go watch Close Encounters of the Third Kind and stay for that laccolith, okay? Right, so you could, now you're working from home, right? You could make a laccolith in your living room like Richard Dreyfuss did in this video, and I'm sure that would really make your parents or your housemates really happy. But here's a better picture of what this laccolith looks like in real life. And the way that this formed is that you had this intrusion of magma in between layers of rocks, and those pre-existing rocks were much weaker and more easily eroded. And so after this intrusion cooled into solid rock, the surrounding rocks eroded away and left behind this really spectacular monolithic tower. Okay, so the next thing, plutons. So plutons, or also called batholiths, are these giant blob-like intrusions that are formed much deeper in Earth's crust. And what they form from is really like the solidification of a really large magma chamber from a volcanic arc or an extensional area where you have a lot of deep melting of the crust. So these batholiths are buried at first, but over time, the landscape above them, the volcanoes that may have formed, the pre-existing rocks overlying the batholith all erode away. And then you're left with these giant rolling hills, typically made out of granite. And these make up the core of a lot of really big mountain ranges in the western United States today. And probably the most famous of these is the Yosemite Valley. So Yosemite Valley is famous for its really impressive topography that was sculpted by giant alpine glaciers during the last few glacial cycles, but that glaciation took place inside of the valleys of a really spectacular granite batholith. And so you can see that most of this rock looks very similar. It's because it's a homogeneous mixture of igneous melt that's solidified into granite. And so it's just a really spectacular landscape that is equally parts due to the igneous geology as well as the glacial history of the area. So, right? Okay. Now, let's also now consider how we describe the types of rocks, igneous rocks that we find. And so we refer to this as texture, right? So this is like how you would like the descriptive way to talk about like what you can observe in an igneous rock. So there's 3 different ways that we classify texture. Whether it's crystalline, meaning that the igneous rock is made out of interlocking crystals that cooled. Fragmental, if it's from little fragments of pyroclastic debris or ash that fell down and then sort of welded together or cemented together. And so you can pick out individual fragments, but they're not crystals. And then glassy texture. And this is a type of igneous rock where there are no crystals. It's just like pure glass. So if you took a hammer to it and shattered it, it would shatter just like if you dropped a glass in your kitchen. So the texture of the rocks, of igneous rocks, tells you about the cooling rate. Because as we learned in some previous lectures, the cooling rate controls how big crystals can get. So in crystalline textures, we have different classifications for the size of crystals we find. If you have a crystalline igneous rock that is phaneritic, it means that there are large crystal grains that you could look at with the naked eye. If you have aphanetic crystalline rock, it's where you cannot see the crystal boundaries with your naked eye. You'd have to use a microscope. And then porphyritic is if you have a mixture of big crystals you can see and tiny microscopic crystals. And crystalline igneous rocks are the ones that we have already talked about, like basalt and granite and andesite, diorite, rhyolite, gabbro, those types of rocks. Those are all crystalline. The fragmental ones, right, the ones that are made out of shards of pyroclastic debris, those can be formed from the deposition of volcanic ash. So a volcano erupts, all this ash comes out and it falls down on the landscape, and it's still really hot, that ash, and so it welds together individual fragments. And then the glassy texture, the ones that don't have any crystalline shapes, it's just an amorphous glass, those are things like obsidian, which is that black, sort of shiny volcanic rock that you can carve arrowheads out of, as well as pumice, which is the really low density rock that erupts out of volcanoes, or scoria. And if you have like a xeriscaped yard, or if you've been out to Arizona, New Mexico, or Colorado, sometimes people's yards, they xeriscape the front yard and they use scoria as rocks to like fill their front yard. It's just like really cheap rock material that you can get for your house. Okay. So the texture and the mineralogy of igneous rocks is critical to their classification, right? So what this diagram is showing is how systematically we understand the classification of our different crystalline igneous rocks, right? So we can think of first the classification, whether something is a fine crystal or coarse-grained crystal, right? Big and small. And the bigger the crystal, the slower the cooling rate, meaning that it's an intrusive igneous rock. So we have higher silica content for granites and rhyolites that decrease towards intermediate melts, which is andesite and diorite, and then mafic melts, which are basalt and gabbro, and then ultramafic, like the ones that have the least amount of silica, which are really a reflection of things that are going on deep in the ocean crust, is peridotite as well as comatite. And comatite is actually quite rare to find on Earth's surface. Peridotite is rare but more common. Okay, and as these different types of crystalline rocks form, right, we have different minerals that accumulate in them. And in felsic ones, we have more quartz, right? That's the high silica content because quartz is SiO2, as well as potassium and plagioclase feldspars. And then we have increasing amounts of olivine and pyroxene in mafic and ultramafic rocks because they have a lot of magnesium and iron in them. Okay, so I wanted to cover that stuff today so that we finished up chapter 4, but now let's jump back into volcanic eruptions so that you guys can do lab 7. All right, so what do we produce during a volcanic eruption? So a way that I like to think about this is, like a pressure cooker, right? You have all 3 phases of matter present in a pressure cooker when you're making some sort of stew, right? Like you have the solids, right? Vegetables or meat, and then you have the liquid, a broth, as well as gases that are escaping steam. And if you build up enough pressure underneath that cap of that pressure cooker and then suddenly release it, stuff's going to fly out, right? And you're going to get all 3 phases of matter. So during a volcanic eruption, which is, fundamentally a release of heat and pressure from the interior of the earth out to the surface, you release solids that include things like volcanic ash or pyroclastic bombs, which are larger fragments of rock that come out. You can get liquids. These are the molten rock, lava that flows out on the landscape. And you also release gas, right? These are the volatile compounds that really don't like to stay in the earth. They want to escape. They're volatile. And these are gases like carbon dioxide, sulfur dioxide, even water, as well as hydrogen sulfide. Okay? So in the last couple of lectures, we've talked about how magma chemistry is important for understanding the type of igneous rock, but also the type of products and their behavior at Earth's surface as lava. And what we can deduce from like the lava chemistry and igneous rock type is the type of explosion and eruption that forms different types of volcanoes on Earth's surface. And this behavior and morphology is really due to the magma chemistry, mostly the amount of silica that is in them, as well as the volatile content, right? So if you have a basaltic lava, which is less viscous, right, it flows more easily, you end up with fissure and shield volcanoes that have a really low slope, right, because lava flows can just flow out very easily across Earth's surface. But as you increase the silica content, right, that lava gets more sticky, and so it doesn't flow as easily, and the profile of these volcanoes becomes steeper and steeper. You're also beginning to erupt more volatiles in these more silica-rich melts, and you end up with more pyroclastic and ash being erupted from the top of the volcano out into the atmosphere. And so as you go towards stratovolcanoes and dome volcanoes, the really steep-sided volcanoes, right, you get less and less lava that comes out and more gas and pyroclastics erupted out of the top. Okay, so the slope of the volcano, as well as the viscosity of the lava and the amount of gas that comes out, these 3 factors really can show you or inform you about the types of hazards that are going to come from different types of volcanoes. So this is actually a clip from a CBS morning news show that actually does a really great job with augmented reality of showing why volcanoes have really different risks associated with them.
The Kilauea volcano in Hawaii destroyed hundreds more homes in 2 oceanfront communities. Dramatic aerial video shows rivers of lava spewing from the volcano. The massive flows wiped out the communities of Kapoho and Vacation Land. Nearly all of the 490 homes are believed to have been lost. These 2 pictures were taken just 2 days apart. Wow. The lava filled in all of Kapoho Bay, extending nearly a mile from the coastline. Lonnie Quinn, chief weathercaster of our New York station WCBS, shows us how Kilauea compares to the volcano in Guatemala. Lonnie, good morning.
Well, Volcan de Fuego in Guatemala and Kilauea in Hawaii are both volcanoes, but they are very different. Volcan de Fuego is a composite volcano. So this looks like your typical volcano. It's tall, it's steep, it's over 12,000 feet tall. Kilauea is a shield volcano. So it's shorter, it's fatter, it's only about 4,000 feet tall. And in Hawaii, most of the eruptions have happened when that lava has traveled 30 miles underground and it breaks through the earth at a number of different openings. Composite volcanoes, on the other hand, these will erupt violently and primarily out of that one main vent. And the lava in Hawaii that's causing all the damage is fountaining at about, well, maybe say 250 feet in the air. And that's because all of that pressure, it's spread out through a number of different openings. It's got a consistency kind of like thick maple syrup, and it travels slowly. This only moves at maybe a half a mile per hour. The eruption from Volcan de Fuego entirely different. It reached 47,000 feet in the air. You've got to think of this as a flash flood. It's filled with rocks and ash, and it just speeds down that mountain at over 50 miles per hour. And outrunning something like this is an absolute impossibility, and people die when they can't escape it because it is over 1,000 degrees, and it is going to burn or it's going to destroy everything in its path. Now, eventually, this turns into like a dense kind of mud, and one thing that both these volcanoes have in common, the danger's not done yet. Okay, at Volcan de Fuego, if it rains, that dense mud is going to cause these landslides called lahars, and they can be incredibly dangerous. In Kilauea, the eruptions just continue, and the scientists think they could continue for another month, if not 2 months more. John?
Lonnie, thanks. I feel like I just went to my favorite science class.
Yeah, great explanation.
Well, obviously that anchor hasn't been to my class, right?
The Kilauea volcano.
All right, so let's start with the different hazards of volcanic eruptions. So the first one, let's go with the most obvious, right? That is a lava flow. So molten rock, it tends to destroy things, right? But it is very slow moving, right? I know I've described this as being low viscosity, like runny maple syrup. You know, I'm talking relative to other types of lava. It's less viscous than other types of lava, but it still is flowing very slowly. And so even though it's flowing very slowly, it is really hot and very dense, and it just kind of crushes and melts everything in its path. Another hazard from this is that once it erupts, it takes a long time to cool, right? It's like if you have just made a massive amount of brownies and taking them out of the oven, and it's just going to take like hours to cool, right? If you erupt out all of this lava onto the landscape, like the surface might look cool, but beneath it, there's still molten rock that may not have cooled yet. And then the other hazard from this is that basaltic lava flows aren't limited to just right next to the vent, right? They can spread out very, very long distances. So this is another video that I think shows a good example of just how destructive this slow flowing lava can be. Oh, somebody's Mustang is getting destroyed. You truly, truly hate to see it. Oh, get that rock off my hood. Oops. Okay, they had to speed it up because this is, you know, watching lava creep is pretty slow. Oh. No, don't come through my fence, lava. Please. I beg you. Please? Oh, I guess you're just gonna come in. Yeah, cool. Alright. Yeah, you weren't invited. Oh, please don't destroy my garden. You can see how it's just slowly moving along, and it's hot, so now it's catching your garden on fire. Alright, so there's a hazard, right? It's just, it buries things and melts them and destroys them. Alright, so lava flows can create another problem, right? Is that this is how the Earth creates new land, right? So when that lava flows out over the landscape and goes out into the ocean, it fills it in, and you create, you know, like a new spit of land. Well, the island of Iceland, right, is, you know, an entire island based on volcanoes. And there was this town called Eldfell in the 1970s that they had this insane volcanic eruption, like that occurred literally next to the city, and this huge curtain of lava from a fissure eruption came up, and it started to flow out into the bay, and this entire city's economy was based on fishing, specifically that this was like one of the few safe harbors in Iceland that you could keep ships protected from really nasty North Atlantic storms. And so what they did is they actually got a bunch of boats and stuck pumps into the ocean and had water guns and sprayed ocean water onto the advancing lava flows to prevent the bay from being filled in. So they were ultimately successful, but something to keep in mind is that the ash that was being erupted from this volcano as well just buried the city. Like hundreds of buildings were just buried in new volcanic ash. So this was quite destructive. And here's another video that it's historical, and it talks about this effort to save Eldfell from the volcano.
At 1:55 on the morning of January the 23rd, 1973, 10 years after Surtsey emerged, Iceland was subject to one of the most famous eruptions of modern times, when, after lying dormant for at least 5,000 years, a volcano on Heimaey, a small island 6 miles off Iceland's south coast, burst into life, threatening the lives of everyone in its shadow. A vast river of molten lava erupted from a mile-long fissure, or cleft, in the ground, and headed for Vestmannaeyjar, the island's port. Fortunately, however, it was moving slowly enough to give the authorities time to start an orderly evacuation of the town's 5,300 inhabitants. 6 hours after the eruption began, most of them were on their way to the Icelandic mainland, either by plane or fishing boat. Around 200 police, fire crews and rescue workers remained, but there was little they could do as the deadly lava flow and 1.5 million tons of ash engulfed much of the town, destroying 350 houses and badly damaging more than 400. Although the lava and other volcanic material had first emanated from a fissure in the ground rather than a mountain, after 2 days it began forming a huge cinder cone. As the cone grew, the lava started flowing from its summit. By the end of February, the cone had reached a height of 600 feet and was expelling a torrent of lava and rocks up to 100 feet deep. As the inhabitants of Heimaey helplessly watched its terrifying onslaught, they named the cone Eldfell, or Fire Mountain. But a few weeks later, as the great 1,000-yard wide river of lava, moving at between 3 and 9 yards a day, looked as if it might reach and destroy the fishing harbor, the main source of the town's livelihood, something had to be done. So, in a desperate attempt to stem the deadly flow, seawater was sprayed onto the river of molten rock to try and solidify it, or at least divert its relentless progress. Specialist pumping equipment was brought in from the US, and a ship with the ability to direct vast amounts of water moved into the harbor. The operation, in which nearly 1.5 billion gallons of water was hosed non-stop onto the lava using 19 miles of pipe and 43 pumps, lasted until early July 1973, when it was judged a success. A short time later, with the harbor saved, the inhabitants of Heimaey began to return. They were faced not only with a massive clear-up of their island, but they also had to set about the daunting task of rebuilding hundreds of houses and other buildings destroyed in the...
Okay, so that is quite a hazard from a volcano, right? Destroying the town and completely changing their way of life. Okay. So a key thing to keep in mind here with volcanic hazards is that the threat from them can extend for hundreds of kilometers away from the actual erupting site, right? And so closer to the volcano where you have lava flows occurring, that is a proximate or nearby threat. But further away from the volcano, right, we can have things like mud flows or pyroclastic flows, which is the sort of mobilization of sediment and rock from really the interaction of lava and heat and water and earth materials to flow downhill and destroy things. And then also the eruption of ash into the atmosphere can deposit it in very thick layers of molten ash across the landscape, up to thousands of kilometers away. And you also block parts of the atmosphere with that ash, which has its own hazards associated with it. So let's go a little bit further away from lava flows and now talk about pyroclastics, okay? So pyroclastics are the materials that are erupted out of the volcano, these big solids, right? A pyroclastic means like a fire for pyro, and fragment meaning clast, right? So it's stuff that's erupted out of the volcano. And so if you're near the volcano when these erupt, it can be really dangerous because you could have like literally a house-sized boulder land on top of you. So I showed this video the other day in class because it shows a really nice example of pyroclastics that erupt out of a stratovolcano in Indonesia, right? So there's the eruption, right? There's ash and debris coming out, and you can see all of these massive boulders that are flying out from the sky and landing on the mountainside below. Right? Some of these boulders that are coming down are huge and massive, right? The size of the entire building. So this is a serious hazard if you have a unit that lives close to the side of a volcano and it erupts. You could literally destroy it with debris that falls out of the volcano. So this video also is good because it shows how ash is out of the volcano as well as going into the atmosphere. Here's another.
This one is coming I think.
Okay, so these pyroclastic bombs are very dangerous if you're in the volcano. And one of my friends in grad school, she is a volcanologist and worked on volcanoes in Antarctica, and she would literally go up to the active part of this volcano in Antarctica, 12,000 feet, sleep up there, and they would wait for the volcano to erupt, and they would go find the pyroclastic bombs that were launched into the atmosphere and landed around the volcano. So they literally were like having to look out for stuff flying out of the sky. She had the craziest, absolute craziest field work that I know of. So anyway, there are some people who are that crazy. All right. So another problem with pyroclastics is that you have all this ash that comes out from the volcano, and volcanoes can produce prodigious, massive amounts of ash and bury entire cities. So the most famous example in history of the negative effects of volcanic ash is from the ancient city of Pompeii, which is below the volcano of Vesuvius in southern Italy. And the really high accumulation rate of ash, as well as volcanic mud flows or lahars that flowed through the city, like literally burned people into place. So this is a fellow who got caught up in sort of the worst possible situation imaginable, where he was melted in place by volcanic ash. And I can't help but think that this is an example where, like, maybe this is like Anakin Skywalker getting melted in lava or something. Anyway, this guy was the chosen one from the volcano of Vesuvius. Okay, so now that's volcanic ash near the volcano, but let's think about volcanic ash once it goes high up in the atmosphere and gets entrained in the atmospheric circulation. Right, so this is Alacoca, which is a volcano in Chile, which erupted a couple years ago, and you can see in this time lapse how it is just erupting massive amounts of ash into the atmosphere. So that ash because it is so fine-grained and light, it's caught up in the winds and it begins to circulate through the atmosphere. So this is a problem for sorry, I'll stop that. This is a problem for global society, right? Because we rely on air travel to get people around, to do commerce, for everything, right? We're seeing the effects of that right now with the coronavirus, that the economy basically starts to falter if we shut down air travel. And the same thing happens when we have massive volcanic eruptions around the planet. And this is showing how NASA
Volcano
modeled the effect of the ash eruption from Calbuco in Chile, and how that ash was distributed in the atmosphere. Okay. All right, now I'll let the video play.
in April 2015, spewing a plume of ash and sulfur dioxide over 10 miles into the air.
Volcanic ash like
this can cause airplane engines to fail, and it can persist in the atmosphere for a long time.
It can be difficult to
distinguish the volcanic plume from ordinary clouds, but NASA scientists are developing a new way to map the full three-dimensional structure of a volcanic cloud, providing improved information for air traffic management.
The concentration of sulfur
dioxide is mapped by the SUNY MPP satellite as it passes overhead, and then looks back, and also measures the vertical profile of the cloud in 3 separate slices.
The location and height of
The location and height of the
as
particles,
the amount of sulfur
dioxide,
is being integrated
is being integrated into
patterns
models of weather
forecast the
patterns
spread
to
of
forecast the
volcanic
spread
cloud.
of the volcanic cloud.
The high resolution of the
The
data
high resolution of the data from the vertical
allows a more
profiles
accurate
allows a more
forecast in
accurate
days,
forecast
weeks,
in the
and months
days,
after an
weeks,
eruption,
and months after
which
an
could
eruption,
reduce airline
which could reduce
cancellations
airline
and rerouting
cancellations
costs.
and rerouting
The
costs.
final product will be
The final product will be available in
for
near
use by
real time
operational
for use by
agencies
operational
making decisions
agencies
about flight
making
safety.
decisions about flight safety.
Okay, so even if you are not close to the volcano, there can be global effects from an eruption, like the ash that gets in the atmosphere that can interrupt air travel. Okay, now let's talk about another hazard, which is a lahar, or a volcanic mudflow. So really the idea here is that when you have molten rock, lava, mixed with water and debris, sediment, rock, organic material from forests, you basically create a hot, devastating slurry that destroys everything in its path. And so these are really dangerous hazards in stratovolcano environments where you have really steep slopes, sometimes with mountains that have glaciers or large snowfields on top. And then you have an eruption that can melt the overlying glacier or the snow, and then send this massive tidal wave or debris flow of a mixture of volcanic and surface material downstream. And so these lahars will follow the paths of the big mountain valleys, but they don't just flow like a river. Like they occupy large volumes of it, and they can go very long distances. So in this oblique image of Mount Rainier, I'm showing the pathways of some of the big lahars that can come down from the summit. And this is important for the city of Seattle and Tacoma, as well as the capital Olympia, because some of these lahar pathways can make it quite far from the actual volcanic peak and make it all the way out towards the coast where a lot of people live. So we can model how lahars will flow across the surface of the earth given a size of eruption and the types of sediment that are on top of Mount Rainier right now. So this is an important thing to consider for communities that are developing in volcanic areas, right? It's a very bad idea to build anything in a potential lahar path because it will completely destroy whatever is there. So in Iceland, they have actually a special word for lahars when you have a really spectacular interaction between the ice cap that sits on top of Iceland as well as the volcanoes that are underneath them. You can actually melt entire glaciers in basically an instant. And this creates a insanely large flood, which in Icelandic is called a jökulhlaup. And a jökulhlaup occurred in 2010 when Eyjafjallajökull erupted quite spectacularly. So this is a helicopter video showing what this looked like, and it is totally crazy. This is watching an entire glacier melt instantly at one time. So we are looking at an insane amount of water and debris that is just rushing across this landscape. Right? This video doesn't do it justice, but we are looking at topography. Like, that's a waterfall of thousands of feet that is just completely melting out a glacier from the erupting volcano underneath it. Right? And so it comes off of the mountainside, all of this debris and melt, and it goes into the river plain below and forms these massive river plains and floodplains. And Icelanders do not build anywhere near these areas. And they typically build bridges that are high enough above these floodplains where they don't have to worry about their infrastructure being cut off as much. But this is a really unique, devastating hazard from volcanoes, is a lahar and sort of a super lahar, which is a glacial flood like a jökulhlaup in Iceland. So another hazard from volcanic eruptions is the release of toxic gases. So what can happen at a volcano at the base of it is that you have an accumulation of gas and volatiles that are accumulating. And if you sort of shake things up, you can release all of that gas out into the atmosphere. And so a really terrible example of this happened in Cameroon in the 80s when these volcanic gases were coming out of vents above this volcano, and they started to just sort of float in a layer at the bottom of a lake, Lake Nyos. And then there was just like this terrible thing that happened where the lake got mixed, right? It got blown in the wind, and it sort of mixed up the gases at the bottom of the lake and brought them up to the surface. And it instantly killed 1,700 people one night. And it was a silent killer. So like people went to sleep that night, and then CO2 came out of the lake and asphyxiated everyone, and they all died. And so people came to the village later and found an entire village that had been just devastated by the release of volcanic gases. And so what they've done in Cameroon at Lake Nyos to prevent this from happening again is they've actually put a pump down onto the bottom of the lake that sort of brings up the gases so you don't end up concentrating a massive amount of poisonous or toxic gases at the bottom of the lake that can be released all at once. And then the worst possible thing that can happen from a volcano is if the entire thing blows up. And we call this like complete destruction from an explosive eruption. So what can happen here is you have a full-blown eruption, and it causes the volcano to bulge and explode in all different ways, and then it collapses back down on itself with the lava all gone, and can create these massive eruption centers called calderas. And so this is common in stratovolcanoes, particularly areas where there's a lot of gas that builds up. And I've shown this video in class before, but this is of a explosive eruption of Krakatoa, or Anak Krakatoa in Indonesia, Papua New Guinea, sorry, that erupted quite spectacularly a few years ago. A huge explosion.
Watch out for the shock, it's coming. Watch out for the shock, it's coming.
These explosives
Molten Toledo.
really devastating, and 1815, Krakatoa, a larger eruption than you have really encountered in the last 100 years. Literally, to be heard 1,000 miles away. and there was a fleet of British sailors who were on an island 200 miles away, and then the entire crew went deaf the rest of their lives from hearing that explosion. The other example of a complete destruction of a mountain that we are familiar with here in the U.S. is the destruction of Mount St. Helens, which we saw the entire side of Mount Helens disintegrate all at once. Okay, so I'll finish up here. Is that flank collapse, when you have complete destruction of a volcano, can be quite devastating, because if you're on a volcanic island or near a large body of water, if you have all of that debris that is suddenly displaced and moved into the water, it causes displacement of water, which creates a massive tsunami. And only a couple years ago in Indonesia, there was a really devastating tsunami that happened in the middle of the night when Anak Krakatoa erupted and its flank collapsed and sent out a massive tsunami that killed hundreds of people in coastal communities away from the volcano. So that's just like most of the volcanic hazards that we need to consider, and we will pick back up with that later on Friday, okay?